Today, I'm going to show you how to do a buffer overflow attack. It's the basis for a disturbingly large number of security vulnerabilities we find nowadays. The buffer overflow attack basically takes advantage of the fact that variables for a given function are stored in memory and sometimes copied. So there's many vulnerable functions in C and Java programming that can be used to overflow the buffer, which by itself would just cause the program to crash, but when used in a very special manner can be used to run whatever arbitrary code you choose. Now, this video is actually a response and an outgrowth of the computer file buffer overflow video, which was originally created by Dr. Michael Pound. So I definitely suggest checking out that video first and then coming back to this one. So, in a nutshell, what is a buffer overflow? Well, if you've ever done C programming or Java programming or really programming of any kind, variables for a function call are stored in memory. That's pretty obvious. What's interesting is the order in which they are stored in memory. So for this video, I'm going to show you how to do this with Kali Linux, which is based on Debian. Now, the details of how memory is stored, how variables are stored in memory, will change a bit between the platform, operating system, as well as how the program was compiled. But for this video, for argument's sake, we're going to assume this. Now, in this image here, which is from sploitfun.wordpress.com, really good website, this is upper memory. This is the highest memory address. So if you have 4 gigs of RAM, this is the top 4. So at the high memory, which is up here on the top, versus the low memory, we can see the stack layout. So first few, don't worry. We have argv, which is the arguments being passed into the function. argc, which is the count, int value, of the number of arguments. The return address, in other words, where the function should go next after it's done running. The caller's EBP, also known as the frame pointer, which is basically saying, now that we returned, where to go back to. A little bit of alignment space because, again, we're dealing with a 32-bit processor or a 64-bit processor, and things generally run faster when things are aligned to the memory address, which is a power of 2, 4, and 8, respectively. And then our buffer. This buffer right here is what we're going to be exploiting. And then way at the bottom, we have the value ESP, which is the stack pointer, which is made to point to the quote-unquote top of the stack, which is actually the lower memory address. So we have the top address and the bottom address. Now, EBP stands for the extended buffer pointer. ESP stands for the extended stack pointer. These are actually register values in the processor itself. So this extends to things like Intel processors, AMD, ARM, and a bit of the Motorola processors. And it's a general way of kind of managing how the stack itself is used and referenced on the assembly level. So now we have all that going. Open up Kali Linux, open a terminal, type in uname -space-a. Now you'll notice I'm actually using the 32-bit version of Kali Linux. The reason I'm doing this is because I want to make this tutorial as quick and easy as possible. So if you want to follow along, make sure that you're using Kali Linux 2016.1 32-bit. You can verify this by seeing the kernel I'm running here, Linux Kali 4.3.0, Kali 1-686-PAE. As long as you're using this version of Kali, you can follow along very quickly and easily. So, next up is if you go to my GitHub page and look for the buffer overflow tutorial in Kali, these are the commands I'll be using throughout this video. So you can see here I tell you to use the specific version of Kali and where to grab the torrent file. Now, buffer overflows have been known about for a very long time, since the 60s, 70s, etc. So there's actually been a bit of security features built into the operating system as well as the processor itself to help prevent these things. So we're going to have to disable a few of these to get this example to work. Again, the example we'll be showing to you is a quote-unquote best case scenario, assuming everything is set up perfectly. But again, this is just for teaching. When you do a real exploit, you're going to actually have to work around these. But for now, let's just turn these off. So the first thing I'm going to turn off is memory address randomization. So you can see here when you do cat /proc sys kernel randomize VA space, usually this will be set to the value of 2. So the way you disable that is typing sudo bash space -c space single quote echo quotation mark kernel randomize VA space equal to 0, and you append that into the etc systemcontrol.conf file. And to reload that, you type sudo sysctl space /p. All right, that's all set. And then you run the command cat proc sys kernel randomize VA space one more time. And as long as this says the value of 0, you're good to go with that. Next up, we need to enable debugging and core dumps. So by default, this will usually be set to -1 or 0. So we have to set that to unlimited, which means unlimited size. Verify that. All right, cool. So we've prepped the OS itself to make it easier for us to do buffer overflows. Now, one thing that's a little bit annoying is every time you run a program, by default, it'll actually be in a different location in memory. And that actually depends on the environmental variables. So if you ever use bash, if you type print env and press enter, this will show you all of the environmental variables that are running around. Don't worry too much about the particulars of this, just know that they're constantly changing. So when you run your program, your memory address will change a little bit too. So let's close that out, type nano. Now we've already copied this from the browser, so we're going to press Control-Shift-V to paste, Control-O, call this env exec.sh. There we go, env exec.sh. Write that out. Type Control-X to exit. We're going to do chmod space +X. This will make this script executable. Nope. env exec.sh. All right, cool. Type ls, and there we go. This should appear as a color of kind of neon green for it being executable. All right. Next up is our vulnerable program. So we're going to copy this, Control-C, type nano, Control-Shift-V, and we're going to press Control-O. We're going to call this vuln.c. Press enter. All right. So if you've never programmed C before, this is actually a very simple program. We're going to include the standard IO, input-output header, which allows us to read and write from the standard library. And then we're also going to import the library for string. That's it. Quick and easy. By default, C programs call the int main function. And the default values passed to that are int argc, which is the count of arguments being passed in, as well as a character pointer to argv, which is a character array of values, basically a string. So, next line, we create a character buffer with 500 bytes, and we run the very vulnerable and very insecure function string copy. This says copy the argv value in the first position, in other words, the first value we pass to argv, and copy that into buffer. Now, the problem with this function call is that if argv is more than 500 bytes, it will quote-unquote overflow the buffer. Now, you can see in this diagram here, we start writing in the lower memory addresses. So when the function is first created, it writes from the high values down to the low values. And the assembly code, I'll show you a little bit later, actually tells it to give itself around 530 bytes. So we start at the lower value here, and we actually write up. So what ends up happening is we actually end up overwriting things like the caller's EBP value as well as the return address. And this is where the danger comes. This is a very insecure function. There's another version of this called string ncopy for C. which will tell you to only copy 500 bytes. String copy by default will continue copying values until it hits a null pointer. I was like a null character, which is usually indicating the end of a string. So that's basically what we're going to be doing with this. So let's go ahead and Control X, exit out, type ls. So you can see here we're in our home folder. We have envexec.sh and our vuln.c program. Now we're going to compile this using the GNU compiler to create an executable file. So again, Control-Shift-V to paste it. Now this is an interesting value because we're using the GNU C compiler and we're telling it z exec stack function no stack protector. In other words, we're actually turning off, again, more of the security features. And we're saying m preferred stack boundary is equal to 2. In other words, try to align things to a 2-byte value. And include the, or I say compile the file vuln.c, include the disassembly comments, and create the file vuln, which is actually going to be an ELF Linux executable. So go ahead and run that, type ls. And there we go, we have the vuln executable. So that's all well and good. In order to properly debug this and make the vulnerabilities work, what we're going to do is call envexec.sh, send it the command -d vuln. What this will do is clean up our bash environment and strip it of every setting possible, and except the ones that are required, and then run the GNU Debugger, GDB, loading up the file vuln. And this will make it a lot easier for us to run the exploit. All right, now we're inside GDB. So I'm going to go over a quick overview of some of the common commands to run GDB. So you can type quit, you're done, press up, back in. You can type Control L, and that will clear the screen for you, nice and easy. You can type list, and this shows you some of the debug symbols. So in this case, we have the debug symbols for C code. And there we go, we can do it based on function calls. We have more than one function. And we can actually disassemble this, or do disass space main. And this will convert the C code. Remember, this will show you the assembly code that's powering the function known as main. So if you look through here, you'll notice a very interesting value. This right here, 0x1f4. So what I'm going to do is go ahead and Control-Shift-C to copy this. We're going to do a hex converter. Go ahead and paste it, convert. And there we go. That's our buffer right there, is those 500 characters. So that's the assembly code defining the buffer. And I won't really go over the specifics of what's actually happening here. You can look it up yourself sometime if you'd really like to. But just know that our string code here, car buffer, is being allocated right there with that assembly call. All right. We get a little bit of info on the operating system, info OS. You can get more details, info OS, CPUs. If you find it interesting, it's nice to help with debugging sometimes. More interesting ones are info functions. So these are all the various functions. So you can see, even though we only defined one main function, there's actually a lot of other sub-functions that are floating around there. Info variables. These are all the global variables that are created by C automatically. So let's go ahead and run and pass with the value hello. This will run the vuln program. There we go. Ran the program and it exited normally. Nothing too interesting. Instead, let's try overloading it and actually causing a crash. So we type in run space $, open parentheses, Python space / -c space, single quote, print space, double quote, /x41, double quote. And this was times 408, single quote, close parentheses. What this is actually doing is the $ parentheses is creating a bash subshell and calling the Python program and -c is the command. So pass Python the command, print x41 508 times. x41 is the hexadecimal for the A character. So because the buffer was defined as being 500 characters, we're going to pass it 508 and overflow it, and this should crash the program. So go ahead and press enter, run the program, and there we go. Program received signal sig seg v. In other words, a segmentation fault. All right, so we just crashed the program, which is a good thing. If you're trying to do pen testing and explore viruses, the most interesting thing you can possibly do is cause a program to crash. Because if you cause that crash, there's probably something interesting in there that you can exploit. So let's go ahead and look at the registers. So info, registers, enter. And again, we're looking back at some of our ESP and our EBP values here, which is very interesting. So again, we passed this thing the value of 41, and you'll notice the EIP, in other words, the extended index pointer, and the EBP, the extended base pointer, have been overwritten with the values 414141. So that's all well and good, but what can we actually do with that? Well, let's look at the memory addresses. Here we can see x/20x, in other words, show 200x characters, parentheses, $ESP, in other words, take the address of the extended stack pointer, go back not only 500 characters, let's go back 550, so a little bit before that. Run that command, and here we go. We can actually scroll through the memory itself. So if you look here at this address, you'll notice it's the very beginning of the 414141 values. If you press down or return, you can start seeing where the buffer itself exists in memory and where it was being overwritten. So that's all well and good. In order to actually make this exploit work, we're going to need to take control of the extended base pointer. The way we do that is we're going to say, instead of typing 41, which is the ASCII character A, we're going to type the character 90. The reason that's interesting is that in assembly, the hexadecimal character 90 is a no-op, in other words, a no operation. In common usage, the no-op command is used purely for padding purposes. It doesn't actually do anything. It literally is the effect of saying, go to next, go to next, go to next. That's it. So because we know that we can crash the program with 508 bytes, we're going to say print 90 426 times, and then we're going to pass it. This is the hexadecimal version of running bin-zsh, which is another shell type synonymous with bash. So in other words, we're going to have the given vulnerable program run another program, and then we're going to pad it out with the values 5151 10 times. What this will do is we'll fill up the buffer, we'll overwrite the alignment space, and our goal here is to overwrite the caller's EBP and the return address with the values 5151. And if we do this correctly, we should see the registers EBP be overwritten and EIP overwritten with the values 51. Copy that, Control-Shift-V, type Y. So again, we segfaulted, but this time the return value was 51 instead of 41. That's useful. That means we were able to successfully overwrite the return address and the caller's EBP. So let's type info registers one more time. And there we go. EIP and EBP have been overwritten. Now, this is good because we know how large the buffer is and how many bytes we have to overwrite afterward to change and control the EBP value. Now, you may be asking yourself, why does this actually matter? It's because the return address and the caller's EBP, we can tell the program is running in memory to actually go to another memory address. And that's cool is, by default, this will go back to the function that called the int main function. But instead what we're doing, instead of going back to the parent function, we're going to redirect it somewhere else. We're going to redirect it back into the buffer. And within the buffer, we're going to be using what's called a NOP sled, a no-op sled. And we're going to pass it the value 90, and we're going to keep sliding it along until it finally hits our shell code to run another shell bin zsh. So one of the things we have to do first is we're going to double check memory to make sure we see things correctly. So copy and paste that, press enter. Here we can see the value 90, so our NOP sled does exist. And we're going to have to choose a value. We're going to have to choose someplace in the middle of a NOP sled here to run. So let's go ahead and pick this value right here. 0xbf ff fa ba. Right in the middle of our NOP sled. So what will happen is, if we can redirect the execution of the program to look at and start reading this value memory, it'll continue sliding until it hits our exploit. So that looks pretty good. Now one of the things we have to do with first is convert this memory address value here into big endian. So we basically have to reverse the order of the bytes. So here we can see bf ff fa ba becomes at the very end bf ff fa ba. So it's not exactly reversing it, but it's similar to reversing it. But anyways, so here we have our exploit from before. So we have the padding for the NOP sled, which includes 425 bytes, our payload, and then way at the end, instead of using the value 5151, we're using the very specific memory address ba bf ff fa ba. So let's go ahead and copy that. Press Q to quit out of this. Control L. Control Shift V to paste it. And if we run this successfully, we should see a new shell come out. Type Y. Oh ho ho ho. So that's pretty interesting. Now it says Kali #, so we can type in things like, who am I? I'm root. PWD. Where's my present working directory? LS. And there you go. We just created a buffer overflow. So again, by default, a buffer overflow will just crash the program. But if you're crafty and malicious and a little creative, you can actually redirect the program to do whatever you want, for good or bad. So I hope this video helped you a little bit understanding how buffer overflows are created, what they're capable of, and generally how they operate. If you have any questions, leave some in the comments. Thank you.